In this lesson, we would understand what is the first derivative test, and also we would understand how to use the first derivative test to sketch the graph of the function when we are given the function equation. The success criteria for this lesson is, after going over the lesson, the students will be able to determine the derivative of the function equation, make the interval table to conduct the first derivative test, sketch the graph of the function using the first derivative test. Otherwise, in the previous lesson, we have already understood how the slopes change for a given function. For example, in this function graph, we know that the slope changes at x equal to 3. Therefore, 3 is the critical number of this graph, as the derivative of the given function, if this is the function, is going to become negative to positive at x equal to 3. This is what is called the first derivative test. So first derivative test always tells us where is the derivative going to change for the given function. Similarly, if the graph opens downwards and this is x equal to 4, the derivative is going to be positive before 4 and the derivative is going to be negative after 4. So if this is the graph of the original function, then its derivative is going to change from positive to negative at x equal to 4. Therefore, 4 is going to be called the critical number. Now let's understand how to make the graph of the function when we're given an equation for the function. Let's say we're given this function x to the power 4 minus 8x cubed plus 18x squared, and we want to use the first derivative test to turn this into the graph. So what would we do is the first step to determine its derivative. The derivative of this equation would be 4x cubed minus 24x squared plus 36x. The next step is to find the critical numbers. To do that, we would put the derivative equal to 0 and we would solve for x. When we have to solve for x for a given equation, we have to turn the equation into factored form. Here we notice we have a common factor of 4x. So we're left with x squared minus 6x plus 9. Since this is a perfect square, we can write it as x minus 3, that is 4x times x minus 3 square, which is equal to 0. To solve for x, we will put each factor equal to 0. So we will have 4x equal to 0. That would give us x equal to 0. And we would have x minus 3 square equal to 0. That is x minus 3 equal to 0. That would give us x equal to 3. Therefore, we conclude that x equal to 0 and x equal to 3 are our critical numbers. As we know, critical numbers are the numbers where the derivatives change the sign. Therefore, we would be using these critical numbers to make the interval table. We can first place the critical numbers on the number line to decide on the intervals. So the first interval is negative infinity to 0, next is 0 to 3, and next is 3 to positive infinity. When we put this in the table, this is how it looks like. And on this side, we would put the factors of the derivative function, that is 4x, x minus 3 squared. Using the values of the factors, in fact, we will be using the signs of the factor values. We will finally conclude what is the derivative sign going to look like. That would give us where the original function is going to be increasing or decreasing. Now to simplify 4x, we would take any value from negative infinity to 0. Let's go with simple value negative 10. If you put 4 times negative 10, we get a negative 40. That means negative sign. We are just interested in the sign of the values. Then we put negative 10 in here, so it's negative 10 minus 3. When we square it, it becomes a positive. Negative and positive, when we take the product of these two, because that's what the derivative function is, we can separate this out from here. So the product of negative and positive is negative. At 0, when we sub in 0 here, 4 times 0 is 0. When we put 0 here, we get a positive answer. 0 multiplied by anything is a 0. When we pick any number from 0 to 3, let's say 1. 4 times 1 is 4, which is positive. When we put 1 here, it is 1 minus 3, which is negative 2 squared. That is a positive again. Product of two positives is a positive. Next we put 3 in here, so 4 times 3 is 12, which is a positive number. When we put 3 here, 3 minus 3 is 0, 0 squared is also 0. Product of anything with 0 is always a 0. We pick any number from 3 to positive infinity, let's say 10. So 4 times 10 is 40, which is a positive number. When we put 10 here, 10 minus 3 is 7 squared, which is positive. Product of two positives, again a positive. Using these signs of the derivative, we're going to conclude what would the original function look like. When the derivative function is negative, the original function is decreasing. When the derivative function is positive, the original function is increasing. When the derivative function is positive, the original function is again increasing. Now, we learned this in the previous lesson that if the preceding interval is negative and the following is positive, we will be seeing a min here. Whereas this is something different and new because both the preceding and the following interval are directing in the same direction. So this point where the preceding and the following intervals are in the same direction is called point of inflection. Similarly, when both the preceding and following intervals are directing in the negative direction, we again see a point of inflection. When we use this table to make the graph of the function, we would first plot these points, that is 0 and 3. Now, in this particular example, since we're given the function equation, that was fx is equal to x to the power 4 minus 8x cubed plus 18x squared. So we can always find the y value when x is 0 and x is 3, so that we can have our exact point of minima and point of inflection. In order to find the minimum point, we would sub in the original function x as 0. When we do so, we notice this becomes a 0. Therefore, f of 0 is a 0, which is this point, and we can mark that point. Next, we can solve for f of 3. That would give us a 27. Let's say this is where 27 is. So using all of this information, that is from negative infinity to 0, our function is decreasing. So we'll start coming from negative infinity till 0, the function is decreasing. It would show us a minimum at 0, 0. After that, it starts increasing. And then it is going to show a point of inflection and keep increasing. So this is how it looks like. So at 3, we would see the point of inflection. It is increasing and then it keeps increasing. Point of inflection is nothing but it's not exactly a turning point. It's just a slight squiggle like this, or it could be like this depending upon what is the preceding and the following interval, or it could be like this, or it could be like this. So we would always show a squiggle. So these squiggles are point of inflections. And this is how the graph of the original function would look like for the given function equation using the first derivative test.